Hello everyone, my name is Molei Tao. It's my great pleasure to be presenting my work at this workshop, and I thank the organizers for their kind invitation and great organization. I also appreciate the fact that the audience and attendees have a wide range of expertise, and for that reason, if certain parts of my talk appear to be trivial to you, I apologize, but hopefully some other audience could find it of some relevance. What I'm going to talk about is a joint work with my student Lin Kai Kong, and it's about the behavior of a popular method used in a popular optimization method used in machine learning, namely gradient descent. And in particular, we wanted to understand what if the learning rate is chosen to be very large, and what we discovered is that if the objective function is actually exhibiting behaviors over multiple scales, then the deterministic iterates can actually appear to be stochastic. So let me start with gradient descent. So it's a popular method for finding a local minimum of a differentiable function f, and to computational mathematicians, it can be viewed as a forward Euler discretization of the gradient flow ODE. And of course, if you want to get a good approximation of a local minimum, then you would want to simulate this ODE to a very large time. So to do so, you would have to use capital T over h steps, where h is basically the time step or the learning rate of this procedure. And therefore, it's very common that people wanted to use a large h because this way you will have fewer steps and therefore more efficient computation. There is one catch though. The catch is that if h is too large, then the gradient descent dynamics, the gradient descent iterates are no longer good approximation of the continuous solution. And here are some simple examples. So on the left, I'm simulating using a very small time step, and then you see that everything works as expected. You have this nice monotonic convergence to the local minimum. If I choose a rather large time step, I still converge to the local minimum, but I get an oscillatory behavior, and the trajectory is not monotone at all. So this is actually rather far from the gradient flow. If I further crank up the time step, my iteration becomes unstable. And these three types of behaviors are not the only types of behaviors. And in fact, if the potential well that we were considering is actually part of a multiscale potential landscape, then much more complicated things can happen. So here I'm simulating this gradient descent in this multiscale landscape using a large time step. And you can see the particle, which represents the values of xk at iteration k, actually exhibits very irregular behavior. It's almost impossible to predict where it'll go at the next step. And in fact, if I plot x as a function of k, where k is the number of iterations, and you can see that the orbit appears to be rather chaotic, or rather stochastic. And here is the histogram of all the values that have collected along this orbit. And you can see that it appears to be some distribution that is actually concentrated around 0, which is the global minimum of the loss function. So it seems that even though the dynamics is completely deterministic, the behavior of the iterations appear to be sort of stochastic. And in fact, if you are familiar with stochastic gradient descent, I would say the iterations actually resemble what you will get out of stochastic gradient descent. The only problem is that we don't even have any stochastic gradient. So do we really have similarity? And my goal of this talk is to convince you, both theoretically and numerically, that yes, you can actually get stochastic behavior similar to that of SGD out of deterministic gradient descent. And in particular, our theory will be in a setup where the objective function is actually multiscale and the large learning rate is used. And in this case, you will actually get what we suspected. And the reason is because the gradient descent dynamics will actually be chaotic, so it sort of induces a pseudo-stochastic behavior. Before I further explain, let me first describe what I mean by being similar to SGD. So first of all, if you start an ensemble of initial conditions, different initial conditions, and then evolve each one according to deterministic gradient descent, and then you look at the distribution of this ensemble at time t, then as t goes to infinity, this ensemble actually converges to some specific statistical distribution. For example, so you see that here I started with uniform initial distribution, and then after 1,000 iterations, I actually get a different distribution. And what is remarkable is that it doesn't really matter what the initial distribution is. In the end, you will always get the same distribution. A second feature, a second observation is that if you plot the histogram of any single orbit, I mean, you plot the values it takes over a long time span, then as the width of the time span goes to infinity, the histogram will actually converge to the same statistical distribution, the same one as before, and it doesn't matter what the initial condition is. In fact, here I plotted the histograms of two orbits starting with different initial conditions, and you could barely see two histograms because they almost overlap with each other. Just for demonstration, here I'm plotting the orbit evolved from one initial condition, so you can see the orbit is rather irregular. And moreover, the limiting distribution can be actually quantified in some sense. It's going to be approximately just the Boltzmann-Gibbs distribution. And all these three features are actually features that stochastic gradient descent also exhibits. More precisely, I was really thinking about over-damped Langevin equation, which is closely related to SGD. And in fact, for example, Professor Wei Nan and collaborators have written beautiful papers that quantify the relations between SGD and over-damped Langevin. And for over-damped Langevin, you can really prove the three features that I just talked about. However, the iterations of deterministic gradient descent is just deterministic. So if you start with the same initial condition, you will always get exactly the same orbit. So this is something that is different from SGD. SGD will actually give you different realizations, but here our stochasticity is really in quotation mark because you still have determinism. So hopefully I explained what I wanted to show you and to demonstrate. Now let me be precise about my setup. So like I said, first of all, our theory requires the objective to be multiscale. And what I meant by that is the loss function is being decomposable into a macroscopic part, such as this landscape plotted here, plus a microscopic loss, which depends on a small parameter epsilon. And one example of this microscopic loss is basically a rescaled version of a periodic function. It's rescaled in a way such that along the spatial direction, you have periods actually at the order of epsilon, and the value of this function is also going to be at the order of epsilon. and then you add this microscopic scale on top of the macroscopic scale, and then you get this overall loss function. Okay, it's actually highly non-convex, and it's multiscale. And I don't want to give you the impression that the microscale has to be very structured. In fact, here is an example where the microscale is less structured. But in fact, the truth is it's actually also structured. It's just that the structure is richer, and therefore the behavior appears to be more irregular. So in this example, the microscale is actually a quasi-periodic function. So just in case someone cares, a quasi-periodic function is basically a combination of oscillations with multiple frequencies. Mathematically, it could be defined as being the evaluation of a multi-argument function, capital F1. So this is really a latent function that is one periodic in each argument. And x is actually multiplied by different frequencies in different positions in the argument, and then you have a combination of all n frequencies. In fact, our theory requires less than those examples. Our conditions are more general. They are a bit technical, but roughly speaking, I first require an O1 first order derivative with a weak limit. More precisely, I look at the microscopic gradient, and I evaluate it at a random variable, at a uniformly distributed random variable along a fixed set. And then I let epsilon go to 0, and if there is a weak limit, if there is a limiting random variable, then condition 1 is satisfied. The second condition is similar. I require that the second derivative will actually be at order 1 over epsilon, and it has some limit as well. So here there's a typo there. It's not a weak limit, it's just a limit. And if you think about it, that's also very natural. For example, if you look at this periodic situation, if you take two derivatives, you get actually 1 over epsilon squared, which after multiplication with this epsilon results in a scale of 1 over epsilon. So that's a multiscale objective our theory will require. And now let me clarify also what I mean by large learning rate. So first of all, what is going to be called a small learning rate? Well, so let's remind ourselves that we are studying gradient descent, which is a discretization of the gradient flow. At least that's how it was came up with. And because the loss admits this multiscale decomposition, the gradient descent iteration is written in this way. And then we can recall numerical analysis, which says that, okay, so if you choose your time step to be smaller than 1 over the Lipschitz constant of the vector field of the ODE that you're trying to simulate, then you get a good approximation to the continuous solution, which converges to a local minimum in this case. So what is the Lipschitz constant of the right-hand side of the ODE, which is basically the gradient of f? Well, it's of course at the order of the Haitian, and the Haitian, due to a second-order derivative of the microscale, is actually at the order of 1 over epsilon, and therefore you need eta, you need the learning rate to be actually smaller than epsilon in order to have a small learning rate that resolves the small scale. And in this case, you would just get convergence to a local minimum. On the other hand, if eta is very large, say it's much bigger than 1, then you can't even resolve the large scale of the system. Even if you discard the highly oscillatory small scale, a gradient descent with a large scale is still unstable. So this kind of learning rate is basically useless. However, in between this convergence to local minimum regime and instability regime, there is some space. In fact, rather vast space, and the regime in between is what I'm gonna call large learning rate regime. In fact, this regime can be split into multiple subdomains. So when eta is large but not too large, you will have something that I'll call local chaos, and then as eta further increases, the chaos will transition into global chaos. And of course, I'll define and talk about these two kinds of chaos. But for now, let me describe to you the main picture of the theory. So we are really just interested in the iterations of the gradient descent map, the deterministic map. But I'm going to be using an intermediate step. I'm going to be actually defining an auxiliary stochastic map on which I will leverage our analysis. So this stochastic map, denoted by phi hat, is almost the same as phi, except the microscopic gradient is actually replaced by this limiting random variable zeta. So let me remind you that zeta is really the weak limit of the gradient, of the microscopic gradient, evaluated at a uniform random variable as epsilon goes to 0. And with this stochastic map, our theory consists of 3 ingredients. So first of all, I will actually show that the invariant distribution of phi approaches that of phi hat as epsilon goes to 0. And this way, if I'm interested in the invariant distribution of phi, I can just look at the invariant distribution of phi hat. And in fact, in the second ingredient, I will actually show the iterations of phi hat converges to a unique invariant distribution. And that invariant distribution is actually approximately Gibbs distribution, of course under certain conditions. And then finally, I have an interesting step where I will actually show that iterations of phi will be chaotic. Of course, if eta is large enough, or equivalently, if epsilon is actually small enough. And why do I want to show chaos? Well, that's because there is a correlation between chaos and the fact that the iteration actually converges to an invariant distribution. The latter, in some sense, is actually stronger. So this is really a correlation, not causality. We actually hope that the dynamics of phi is actually mixing. But proving mixing is oftentimes very difficult, and we don't know how to prove it here at this moment. So all we can show is chaos, and therefore, in some sense, there is a significant gap in our theory, and more precisely, the kind of chaos that we will be showing is called Lee-York chaos. And it's actually proved that if you have weak mixing, then you have Lee-York chaos. And therefore, what we will show is actually a necessary condition for mixing, for what we really wanted. But is Lee-York chaos enough? Is it also a sufficient condition in our specific example? Well, we don't know. So if you are interested in this problem, I'll be more than happy to talk to you more about the details. But anyway, that's a roadmap. Basically, I wanted to study the invariant distribution of phi, and I leveraged that on phi hat. So therefore, let me first tell you why we have the first ingredient. namely the approachment of invariant distributions of phi to that of phi hat. For accuracy, let me actually explicitly write down the subscript subscript epsilon after phi, because the phi map really depends on epsilon, but phi hat map doesn't. And the main step for showing so is the following. So first of all, we have to choose an appropriate function space. That's a space that contains densities that we're interested in this discussion. This is just a definition, although you do have to choose the correct function space. And then we need the existence of invariant distributions for phi, or more precisely, I need that there exists a sequence of invariant distributions for different epsilon values that converge to 0. This is something, like I said, assumed, because we can only prove chaos, which is actually a necessary condition for this assumption. And then we also need the existence of the invariant distribution of phi hat, and this is actually something that can be proved, and I will actually do it later. The key step, I would say, for what we are doing here, namely convergences of the invariant distributions, is to actually show that you give me any distribution, any density in the function space, the push forward of this density, respectively by phi epsilon and phi hat, will actually be arbitrarily close to each other if epsilon goes to 0. And finally, I need to establish some good properties of curly f, such as completeness. This is provable, but I'll skip it. And then, but as Azila-Ascoli lemma in functional analysis, I can actually find a subsequence of invariant distributions of phi as epsilon goes to 0, such that the limit of this subsequence of invariant distributions actually exists. And this very limit is exactly what we want. That's the invariant distribution of phi hat. Okay, so that's why the invariant distributions of phi epsilon will actually converge to that of phi hat. Converge has a quotation mark because really what we have is a subsequent convergence. So, like I said, the key step of this proof is really to prove that the actions of these two maps are almost the same. So, so let me now try to describe the intuition behind this result. So for easy understanding, I'll only be describing periodic microscopic potential, microscopic loss, and showing what is being boxed relies on a key lemma, which is that, okay, you give me an arbitrary density mu0, I can find a nearby density mu in a slightly larger function space such that mu and mu0 are very close to each other, and moreover, the push forwards of this density by phi hat and phi epsilon will be O epsilon away. Okay, so if we can show this, then by taking the limit epsilon of epsilon going to 0 and also some triangular inequalities, we can prove what is being boxed. So really, we just need this lemma, and its proof is actually constructive. So first of all, choose a random variable x0 distributed according to mu naught, and then we pick a uniform random variable, uniform over a period of the microscale, and then rescale it by epsilon, and then add the result to x naught. And the resulting random variable called x will have its distribution. That is what we wanted. Okay, so its distribution is going to be actually mu. And it's easy to show that mu and mu naught are actually very close to each other, O epsilon close. And the remaining challenge is to show that that phi epsilon of x and phi hat of x are actually be O epsilon away. And more precisely, I want to show that for any test function f evaluated at phi epsilon and phi hat, the expectation that their expectations will actually be O epsilon away. So if you think about it, the sole difference between phi epsilon and phi hat is that in phi hat, the microscopic gradient is replaced by the limiting random variable zeta. And the difference between the gradient and zeta can actually be order 1. But as we take the expectation of test functions, we actually average over this uniform random variable, which is equivalent to averaging over a period. If we do so, then the difference between these two terms will actually be reduced to order epsilon at most, and the intuition is that this zeta is really the weak limit of the gradient, of the microgradient, and that's basically the average of the microgradient over infinitely many periods. Okay, so that's the intuition behind this key lemma, and therefore the proof of the first ingredient. So so that's why the inverted distribution of phi can actually be very close to that of phi hat, and thus we now study the inverted distribution of phi hat. Let's recall that phi hat is really this auxiliary stochastic map defined here, and we just want to understand its limiting distribution. Of course, there are related questions such as whether the iterates actually converge, what is the rate of convergence, and all these can be done, although not in a trivial way, because it's important to notice that phi hat is not the discretization of overdamped Langevin. The key difference is that here the noise is actually not Gaussian. It's a bounded random variable. So the most standard way of analyzing the Fokker-Planck equation for convergence does not directly apply here. But we do have results, and one of our results is the following. If f naught is strongly convex and regular enough, then iterates of phi hat, of course with IAD zeta, will actually be geometric ergodic, meaning that the iterations will converge exponentially fast to a unique inverted distribution, as long as eta is not too small. Moreover, if the noise is actually isotropic, meaning that it has a covariance that's essentially a scalar, then the invariant distribution can be actually analytically approximated. It's going to be actually just a Boltzmann-Gibbs, so this is the density of Gibbs distribution plus a small correction. And in fact, if you are familiar with overdamped Langevin, this inverted distribution is precisely what you would get if this zeta is replaced by a Gaussian random variable. More precisely, a white noise process. How we prove this result? Well, so first of all, we use the tool of random iterates to establish ergodicity. And then we use a coupling argument to actually get an estimate of the speed of convergence of this process. Notice that I cannot start directly with coupling because without step 1, I don't even know whether there is an invariant distribution. and then I can't couple. I don't know what to couple to. But now I have the estimate of the convergence speed out of coupling, and this gives us some information about the spectrum of the infinitesimal generator of this Markov process. And at the same time, a direct computation can show that Boltzmann-Gibbs nearly satisfies the invariant distribution, meaning that, okay, so if you take Gibbs and push it forward by phi hat, you will get Gibbs plus a very small error. But what we really wanted is to solve the invariant distribution. So we want to know what distribution gets pushed forward to exactly itself. So we sort of have to invert the inverse equation. But with the help of the spectral gap established in step 2, we can also show that the invariant distribution, from the fact that Gibbs nearly satisfies the invariance equation, that the solution is also nearly Gibbs. Okay, so this is how we worked out the second ingredient. Namely, we gained understanding of the invariant distribution of phi hat, as well as the convergence towards it. The last step is to show that phi iterates are actually chaotic. And more precisely, I originally phrased it as we want to understand its chaotic behavior when eta is large enough. But this is actually completely similar to showing that if epsilon is small enough and eta is fixed, then we have chaos. Okay, so that's something that we're gonna show. And one of our results is the following. Under very mild condition, I just need f naught to have one stationary point at least, and also that my microscopic potential has to be having a gradient that is not zero everywhere. Not zero with probability 1. And then I can find epsilon. So I can find small enough epsilon such that the iterates are actually chaotic in a sense of Lee York. Importantly, there is a strong requirement in this theorem. The rest is actually very mild. That is to say, it only works in 1D. But suppose we work with 1D for now. What is chaos in Lee York sense? Well, so first of all, you can find a periodic orbit with an arbitrary period. Okay, so you give me a positive integer k, I can find a k periodic orbit. Moreover, you can find a rather large set that is actually a chaotic set on which any 2 points will meet and separate each other infinitely many times. And in addition, any chaotic orbit will separate from the periodic orbit infinitely many times as well. So this is the precise statement of the common understanding of anything is possible in chaos. How do we prove this theorem? We basically relied on a powerful result of Lee York, which basically requires you to find 4 iterates, A, B, C, and D, such that the last iterate is actually going to be less or equal to A, strictly less than B, and strictly less than C. Well, you can also do it in the completely backward order. But if you can find them, then the map actually induces Lee York chaos. And indeed, we can find them for the specific gradient descent map that defined above using a little bit of analysis. So this is really not the key step. So I'll just skip the details. But like I said, even though Lie chaos is some very rich dynamics. This theorem is restricted because it's just for 1D. We do have a multi-dimensional result, but it's weaker. So we have to assume that phi dynamics is ergodic, and then we can actually have a quantification of the Lyapunov exponent. The general result is really this line, but for intuition, let's consider a special case where the microscopic loss is actually periodic. And in that case, lambda, this Lyapunov exponent, actually admits this approximation. And if you think about it, a positive Lyapunov exponent is often correlated with chaos. Or more precisely, if you have a negative Lyapunov exponent, you cannot have chaos. So it's really a positive lambda is a necessary condition for chaos. And if you look at this expression, if eta is too small, then this log actually gives a large negative value, and therefore the Lyapunov exponent is negative. So you can't have chaos in that situation. Only when eta becomes at the order of epsilon or greater can you actually have a positive Lyapunov exponent. So this result sort of quantifies when chaos can actually happen in our system. And again, you need large learning rate. A little bit more about the chaos that we have in such a system. So the chaos actually onsets via the usual route. It's basically a series of period doubling bifurcations. So what is plotted here is what is known as a bifurcation diagram. Basically, when eta is small enough, the only stable structure in this dynamical system, in this discrete dynamical system, is the stable fixed point corresponding to the local minimum of the overall loss. But as eta increases, this fixed point actually loses its stability. It's no longer stable, although it's still a fixed point. The stable structure actually bifurcates into a stable a stable periodic orbit of period 2. And then as eta further increases, you have more and more bifurcations. The periods keeps on increasing, and the dynamics quickly cascades into irregular motions. And all these are actually what happened in what I call local chaos region, because this all these things actually happen within a local potential well that is given by the microscopic potential of the overall potential. And in fact, if you restrict your map to an appropriate interval, subinterval of the potential well, then you can actually get a unimodal map. So for those who know, therefore you actually have a rather good understanding of the chaos. It's via the universality theory. But that's not it. That's not the end of story. As eta further increases, then you enter the global chaos region. And this regime is really equivalent to the epsilon going to 0 regime, because really all you care about is the ratio between at least all it matters. The ratio between eta and epsilon is what matters. But this regime is actually something that we already previously discussed. For example, if F0 is strongly convex, then we do know what the deterministic gradient descent iterates converge to. They actually converge to statistically this limiting distribution of nearly Gibbs. And if you take a close look at the Gibbs distribution, it only depends on the macroscopic potential. it only depends on F naught, but not F1 epsilon. And what that entails is that, okay, so this is an example of the actual loss. The macroscopic potential is actually complicated by a lot of local minima due to the microscopic potential. But as gradient descent actually converges to Gibbs governed by F naught only, the limiting distribution doesn't see any of those local minima created by the microscale, and the long-time X dynamics will just sample from the corresponding Gibbs distribution, which means that, okay, so all those local minima can actually be escaped. And the escape mechanism is not due to noise. There's no noise at all. It's a pure effect of large learning rate. So this is one implication that is hopefully relevant to machine learning. But of course people may ask, well, maybe mathematically that's nice, but in practice not all losses are going to be convex. That's true, but I want to emphasize again that I only require the macroscopic part of the loss to be strongly convex. The overall behavior, however, is still non-convex for this result to apply. But nevertheless, let's also talk about non-convex macroscopic potential. So that's actually the interesting case, because for this case, the gradient descent behavior may be different from that of SGD. More precisely, you can still escape shallow local minima of F naught, but you cannot escape deep ones. So this is very different from what you will have in SGD, where all local minima can be escaped, just with different probabilities. And roughly speaking, the reason is that here we don't really have a notion of noise. Our noise really comes out of determinism, and I will explain more about this by a simple example. So here, F naught is an academic double well potential, and my microscale is just some easy microscale that was chosen arbitrarily, and here I choose the scaling parameter in front of F naught to be a rather small value, and then you see that if I start my initial condition to be concentrated in the right potential well, after 10,000 iterations, the ensemble actually becomes very closely approximated by Boltzmann-Gibbs. Okay, so you have a lot of densities in the left potential well, a lot of densities in the right potential well as well. However, if you make K much bigger and do the same thing, so same initial distribution, and then after a long time, all the densities are actually concentrated in the right potential well. There's nothing that escapes to the left potential well. And this is not because I didn't run the evolution for long enough. This is really intrinsic to gradient descent dynamics. And roughly the reason is that when K is very small, the effect of noise is rather strong. So after comparing these two, what you have here, this potential well, is really a shallow one. Whereas if K is changed to a much bigger value, you actually have a deep potential well. So what is the intuition between different abilities to escape from shallow or deep potential well? Well, so let's again consider overdamped Langevin as an approximation of SGD. So in overdamped Langevin, you can always have a realization of a sequence of noises that point to the same direction, and that will allow you to basically overcome any potential barrier It's just that the probabilities can become increasingly small. However, in large learning rate gradient descent, the noise is really coming out of this microscopic gradient, and therefore they are actually correlated. In fact, they are deterministic. But let's just say the noise are correlated, and then sometimes it's actually impossible to have a sequence of noises that point to the same direction. So you really need individual noise or a short burst of noises to be large enough to overcome a barrier, to cross a barrier. But at the same time, the noise that we have here is actually bounded. So there's a maximum strength it can reach, and therefore if the barrier becomes too high, then it just can't be escaped. So that's just the intuition. We do have a quantitative analysis, although that's only for one dimension. That's only for one dimension. It's a little technical, so I'll skip the details. But hopefully you already start to see relevance to machine learning. There's actually one more relevance that I want to add. So really one should be asking a key question, which is that in your machine learning application, is your loss multiscale? And our definition of a multiscale loss is very precise. So we need this macro-micro decomposition, and also we need the microscopic part of the loss to be actually having a convergent gradient, as well as a 1/epsilon order second order derivative. And sometimes these two conditions may not be satisfied, even though they are actually rather general. And in this case, we still observed stochasticity. So the theory is certainly not including all the situations. So what is unclear is whether you will still have approximate Gibbs distribution, and I would say that it's unlikely you will still have it, but there are certainly cases where condition 1 and 2 are not met, but we still have stochasticity, and in fact here is one. So this is about the training of a neural network. More precisely, it's a small, relatively small feed-forward neural network that we train on some UCI data set to do regression. And our training, of course, uses a large learning rate. And then we saw that instead of having the loss convergent to actually a minimum value, the loss actually exhibits this histogram, and it's not even unimodal, as you can see. That's because, of course, the energy landscape of a neural network is actually non-convex. This is the histogram of a weight parameter, and this is a histogram of a bias parameter. You can see it's certainly multimodal, and this is the orbit of that bias parameter. So you see it doesn't really converge to a value, but to a distribution. So yes, you will still have stochasticity in the training of at least some neural network. Do we have any theory on that? Well, we have some preliminary results. Roughly speaking, we believe that if the training data is actually multiscale, which is not a very stringent assumption, because usually data correspond to small fluctuations around some macroscopic mean. So if the data is multiscale, then in certain setups, the loss can be multiscale as well. Note that this is actually not trivial, because the loss is a function of the network parameters. It's not a function of the data. But still, that's possible. So again, if you want to know more, I'll be very happy to discuss with you. Another question is, why did we use UCI data, airfoil self-noise data set, but not the more popular data sets such as MNIST? Well, the reason is that we actually use gradient descent. So our batch is really the whole data set. We don't have any mini batch, otherwise it becomes stochastic gradient descent. And therefore, each step has to evaluate the gradient over 60,000 data points, and our laptop just can't handle that task, and therefore I don't know what will happen if you train for MNIST using a large learning rate. But there are other questions that can be interesting as well. So for example, I showed that gradient descent, which is an optimization method as designed, can nevertheless exhibit stochasticity. But is stochasticity unique to gradient descent? What if I add momentum to gradient descent? And the answer is that we numerically still observe stochasticity if the learning rate is large and the loss is actually multiscale. So here is a simple demonstration. I've noticed just this simple quadratic. The microscale is again some periodic oscillations. But even though this is a one-dimensional potential, the iterations will actually be in 2D because momentum is introduced. So that's why the analysis is actually hard. But numerically, we did observe stochasticity. So again, uniformly distributed initial condition gets evolved into this limiting distribution. If you change the initial distribution, you will get the same thing. And the histogram of an orbit also agrees with the limiting distribution. One orbit looks like this. And what I showed you here is the experimental result of heavy ball method, which is one popular way of adding momentum. It's not the only way to add momentum. Here is another way. NEGSC stands for Nesterov accelerated gradient for strongly convex functions. That's another popular way to add momentum. And you still have stochasticity. The variance of the limiting distribution is different from the one above. For good reason, roughly speaking, it's just because as rescaling effect of the step size, but you again have stochasticity. Okay, so let me summarize what the main message is. So I showed that deterministic gradient descent can nevertheless exhibit stochastic behavior if the objective function is actually multiscale. And this actually happens when you use a large learning rate. And here, by large, I meant the learning rate cannot resolve the microscopic scale, but still it can resolve, it's small enough to resolve the macroscopic scale. And the stochastic behavior is really due to the fact that I have chaotic dynamics. And in terms of implication, for example, if you look at the macroscopic part of your loss, and that's going to be strongly convex, then the behavior of deterministic gradient descent with large learning rate actually resembles that of SGD, and in particular, you can actually escape any local minimum because all of the local minima are actually created by the microscopic potential. And you can actually escape those local minima because we know that the limiting distribution is approximately Gibbs distribution, which do not see those local minima. So if you want to sample Gibbs, you have to have a way to escape all those local minima. But if the macroscopic part of the loss is actually non-convex, then very interesting thing can happen. So shallow local minima created by the macroscopic part can also be escaped. But if there are deep ones, then they just can't be escaped at all. So this is a situation that is significantly different from that of SGD. And I think that's all I wanted to say. Thank you very much, and I welcome feedback. Thank you.